All right, that should be good. So how's everybody doing today? Good. Yep, maybe. All right, some quick announcements before we jump into things. So I've been looking at the amount of work that we covered so far since our second exam, and I realized that according to your syllabus right now, you've probably noticed that exam 3 is stated for next Thursday, right, the 15th. I'm going to push that 1 week later to the 22nd, and I'm going to update the syllabus online on ACE. Similarly, I'm going to push this Jupyter Notebook 6 here. That's due on that Sunday for that week 14, basically to the Sunday before finals week. So exam 3 and Jupyter Notebook 6 will both get pushed 1 week forward. So let me just write that down. So announcements. We have now exam 3 on I think it was the 22nd. Yep. And then Jupyter Notebook number 6, Sunday before finals. In other news, I graded your exams. So exam 2 has been graded. And let me just finish writing this. And I took a very, very generous path in grading that. Your scores are all on ACE if you want to take a look. So what I mean by generous? First, all of those alternative problems that I mentioned that I said, you solve this, you get a maximum of 10 points. I just figured, you know what? If you were able to solve that, sometimes they're all pretty much equally as difficult as sort of the more difficult version. So I said, if you could solve the easier version, you still get 15 points. And then I was very generous with like people who missed stuff. I didn't take out a lot of points for questions. And then for number 7, it was very lengthy to prove that the two wave functions were orthogonal. It's a very lengthy calculations. And really only one person, if I had graded it, one person would have gotten it correct. So what I ended up doing instead was just to give everybody full points for number 7. So number 7, everybody has full points. The other ones, I graded it very generously. Your scores are on ACE. I will return your exams to you on Thursday. In terms of extra credit on that, even you can still get extra credit on it if you want. What I'll do, and I'll make this announcement on Thursday when I return your exams. So if you lost any points from questions number 3 through number 6, right? So not 1 or 2. You can do a few things to earn points back. You can if you wanted to earn points back on those, what you can do is write a paragraph on why you got it wrong. Basically, sort of what mistakes you made and how you would go about identifying those mistakes for future problems. And then, so you need to do that, and you also need to actually solve it correctly. So you do these 2 things, and you'll earn up to half the missing points for that question. And so what you can do is submit this along with your exam 2 so that I can actually like know whether whatever you wrote makes sense for the problem that you actually got wrong. The following Thursday, if you want to get those half the amount of missing points back. So most of those questions are for 15 points. So let's say you got 12 out of 15 for that question, you could earn up to 13.5 points. So 1.5 points back, essentially. So what this does is it's a lot of work for if you only got 1 or 2 points off, it's a lot of work for very little points back. But if you miss a lot of points for that question, you know, you might want to do it. So I'll leave this up to you to see if you want to do it. But like I said, I promised you guys I will do something for extra credit, and that's what it's going to be. So on Thursday, I'll return your exam to, and you guys could decide whether you want to do this or not. Sounds good? All right. So yeah, that's it. Your exam 2 is already in there. If you have questions about it, let me know. But because I'm doing this little explain why you got that question wrong, I didn't put a lot of notes in your little exam 2 while I was grading it, because I want to see if you could try to figure out where you went wrong.
When did you say that the extra credit was due?
So I'm returning your exam 2 this Thursday, and the extra credit stuff will be due the following Thursday.
Okay.
All right. Any other questions on that? Nope. All right, so last time we met, we finished up what we call the 3D rigid rotor, or as some people call it, particle on a sphere. And just to summarize some of the things we went over there, the wave function for a particle on a sphere depends on 2 angles, phi and theta, right? And the wave function looks something like this: 1/square root of 2 pi e to the I m phi times the normalized associated Legendre polynomials that depends on these quantum numbers L and ML, right? And then this M here would be that same ML. So your wave function depends on these 2 numbers, L and ML. So that's the particle on a sphere. We looked at the square of the total angular momentum, right? And this comes out to be L into L plus 1 times h bar squared. So if you do apply this to the same wave function, that's what you get back. So that means that the angular momentum itself is the square root of that thing, everything in the box that I just drew. So L plus 1 and times h bar. And then we also looked at one component of the angular momentum. By convention, it's z, but it could be x or y. And that came out to be, so if you apply this to the wave function, you get ml times h bar. Sounds good? So that's particle on a sphere. Those are all the different, those are all the different operators we applied to it. One of my fire smoke alarms beeping. Sorry, I don't know if you guys could hear it. Can you guys hear it? Yeah. All right. Give me 2 seconds. I'm gonna go make it quiet. Sorry about that. I'm back. Sorry about that. It was very distracting for me. I'm sure it was for you. Smoke alarm silent. I just need to buy new batteries for it. All right. So particle on a sphere. So we've done particle in a box, particle on a ring, particle on a sphere, harmonic oscillator, particle on a spring. Time to actually look at a real system. And so today we're going to look at the hydrogen atom. No model systems anymore. Here's a real system, a hydrogen atom. So in this section here, some of our objectives. we're going to write the Hamiltonian for hydrogen like atoms or ions, and we'll talk about what we mean by hydrogen like. We'll write the wave function, pretty much the same set of stuff that we've done for the other systems. We write the Hamiltonian, we write the wave function and energy of an H-like atom. And then once we have those, we'll calculate other properties. Calculate properties using H-like wave functions. So that's what we're going to do. Those are the steps that we've always taken so far. We write the Hamiltonian, we try to solve the Schrodinger equation to get the wave function, which also gives us the energy. And then once we have the wave function, we can find other properties. So let's start with the Hamiltonian. So let's look at the Hamiltonian. And I'm going to introduce this other concept called the Born-Oppenheimer approximation. All right, so here's where we are. We're looking at a hydrogen atom. Now, whenever you want to write the Hamiltonian of every system, you need to think of all of the parts. What are the parts of a hydrogen atom? Well, a hydrogen atom only has two parts, a proton and an electron, right? One proton, one electron. So here's my proton. I'm just drawing it there. It doesn't matter where it is. Here's my electron, right? Those are the two parts. The proton has mass mp, and it's somewhere, right? So it'll have coordinates x, y, z, right? For now, I'll say those coordinates are xp, yp, and zp, right? Just p for proton. Similarly, the electron has mass me and has coordinates xe, ye, and ze, right? Now, we don't know where the proton is and where the electron is, but let's say they're separated by some distance. We'll just call it r for now, right? It could be very close, it could be very far, it doesn't matter. We're just drawing up the system of a proton and electron to write the Hamiltonian. So let's do exactly that. Let's write the Hamiltonian. We know the Hamiltonian is the kinetic energy plus the potential energy, like that. So let's look at the kinetic energy. Kinetic energy, there are two particles, so there's going to be two kinetic energies, right? There's going to be the kinetic energy of the proton and the kinetic energy of the electron. So let's look at that. So the kinetic energy is, remember, it's negative h bar squared over 2 times the mass times this del squared thing. So if it's for the proton, the mass will be the mass of the proton, and this del squared thing will be the del square for the proton, right? In this example, it will be d squared dx for the proton squared plus d squared dy for the proton squared plus d squared dz for the proton squared, kind of like that. So this part here is the kinetic energy for the proton, and then we have the same thing, except this is mass of the electron, kind of like that. That's the kinetic energy of the electron. So kinetic energy of proton, kinetic energy of electron. Everybody with me so far still? All right. Now time for the potential energy, V. Now we looked at this, we mentioned this earlier, the potential energy from Coulombic interaction is the charge of one species times the charge of the second species divided by 4 pi e naught, 4 pi epsilon naught times r, where r is the distance between them. This is why I used r here as a distance between them. So this is any Coulombic interaction between any two particles with charges, right? If they have the same charge, then this Coulombic potential is positive and they repel each other. If they have opposite charges, this whole term comes out to be negative and they attract each other. So in this expression, anything with sort of positive energy means they're going to repel. Anything with negative energy means they're going to attract. So for this system, the charge on a proton, Q for the proton, is positive E, and the charge for the electron is negative E, where E is the elementary charge. And we're going to use E is equal to, well, the value for E is equal to 1.602 by 10 to the minus 19 coulombs. That's the elementary charge. A proton has positive E in charge and an electron is negative E. So the potential energy between these two would be positive E times negative E comes out to be, for Q1 times Q2, comes out to be negative E squared, right? Divided by 4 pi E naught or epsilon naught R. That's the potential energy. That potential energy. So if we want to write the whole Hamiltonian, it goes the kinetic energy of the proton. Let me write that a little bit nicer. Plus the kinetic energy of the electron, plus the potential energy between the two, which is negative E squared over 4 pi epsilon naught R. I'll make that bigger so you can see. So that's the Hamiltonian of our hydrogen atom. I see people still writing, so I'm waiting. And we've just drawn a hydrogen atom, but you could play the same game for any atom or really anything in existence, where let's say, and we're going to look at an example of this later on in the semester. Let's say you have a positive charge there, a negative charge here, a positive charge here.
Hey,
Somebody says something? No? All right. Each one of them with their own mass. That could be mass 1, mass 2, mass 3, right? Each one of them has their own coordinates, x1, y1, z1, and so on. You can figure out all the various like interactions between them and try to write the Hamiltonian for that system. But this is our Hamiltonian. So we know that we take the Hamiltonian, we multiply it by the wave function, we should get the energy times the wave function. That's the time independent Schrodinger equation. That's the equation we need to solve, right? Now, what should be the coordinates of this wave function, right? Let's look up all the way at the most recent example that we did. We looked at a particle on a sphere, and we said that this particle should depend on, because we did it in polar coordinates, right? It should depend on these two angles. And so those are two angles that ended up being in the wave function. Those coordinates specify the coordinates of the different particles, right? In this case, it was just one particle on the sphere. For the hydrogen atom, there are two particles. So the coordinates for this wave function should be dependent on the x coordinate of the proton, the y coordinate of the proton, the z coordinate of the proton, the x coordinate of the electron, the y coordinate of the electron, the z coordinate of the electron. That's a lot of coordinates, right? So that's where we stand. We need to find a wave function that has 6 different coordinates in it. Now, just like we did for so many different wave functions before, where we're like, these are two variables were too many. So we separated into a part that depend on one variable and another part that depend on the other variable. We're going to do a similar thing. We call this separation of variables, right? We're going to do a similar thing, right? We're going to say that instead of this big wave function with all of these variables, let's separate it into 2 wave functions. We'll have a wave function for the proton, and that will only depend on the position of the proton, the x, y, and z position of the proton, and times a wave function for the electron, which will depend on the x, y, and z positions, coordinates for the electron. We separate out those 2 wave functions. This idea here, being able to separate that out there, is called the Born-Oppenheimer approximation. And I'll show you just a little bit about how this approximation comes into use. So has everybody still with me? All right. So earlier in the semester, we talked about how when we have 2 things working together, we can simplify the whole system by talking about the reduced mass, right? So let's look at the reduced mass in this case, right? So remember, the formula for reduced mass is 1 mass times the other mass divided by 1 mass plus the other mass, right? In our example here, our 2 different masses are the masses of a proton and an electron. So let's say mass 1 is the proton, mass 2 is the electron. We end up with that, right? Now, we all know that a mass of a proton is about 2,000 times heavier than the mass of an electron, right? So if you take the mass of the proton and you add the mass of the electron to it, it doesn't really change much. It's still about the same as the mass of the proton, right? The proton is so much heavier than electron that the proton mass plus the electron mass doesn't really change. So this whole bottom here is kind of like approximately the mass of the proton. So this reduced mass is approximately the mass of the proton times the mass of the electron divided by the mass of the proton. And then we figure out that we can cancel this. So the reduced mass is approximately the mass of the electron, just because the mass of the proton is so much heavier. What does this actually mean from a sort of solving this point of view? Well, it means that the proton is so heavy that when we're thinking of motion, how the hydrogen atom moves, the motion of the proton, the motion of the electron, the proton moves so much slower than the electron that if we want, we can just consider the motion of the electron only. So what that says is we can separate these 2 wave functions into 2 parts, but the proton barely moves, so we can ignore this whole bit. And so in short, the Born-Oppenheimer approximation lets us ignore the motion of the proton in this example, but really the nuclei once we apply it to other atoms. That's the Born-Oppenheimer approximation. We're saying that the nuclei of atoms are so heavy, so slow, the electrons move so much faster that we can just ignore their motion because, from the perspective of an electron, if you imagine yourself as being an electron, they move so slowly that they might as well not be moving. So we can ignore them, right? So going forward, all we really need to worry about is what is the electron part of the wave function for a hydrogen atom, right? So if we were to write this Hamiltonian again, just for the electron part, and I'm going to put an E here for just the electron part, it'll be the kinetic energy of the electron plus the potential energy. That doesn't change. And the kinetic energy of the electron is negative h bar squared over 2m times the mass of the electron times this nabla squared for the electron plus this negative e squared over 4 pi epsilon naught r. All right. In reality here, this shouldn't be me, it should be the reduced mass. If you want to be exactly technical about it, it should be the reduced mass. So that's what we have. In most cases, I'm going to write it out explicitly. In most cases, that's approximately equal to the electron mass if we use it there, kind of like this. So let's look at this system. Any questions so far about this? No, it all makes sense? All right. So we imagine a proton, but it's fixed now. It's not moving, at least not from the perspective of electron. We have our electron and our electron's moving. Who knows what it's doing? I don't know. It's going everywhere, right? The electron, we said, has coordinates x, y, and z. I just dropped the e for now. But we also are concerned about this r coordinate, right? The distance between the proton and the electron, because that comes in here, right? So instead of working with x, y, z, what we're going to do instead is just be like, hey, let's just transfer everything into polar coordinates because we already need the r for the Coulomb interaction anyway. So let's transfer everything into polar coordinates. So now, so when we transfer to polar coordinates, if you remember, for 3 dimensions, those coordinates are r, phi, and theta. So this is what we call Cartesian coordinates. We want to transfer them into polar coordinates. Let's do chords like that. Because it's going to make life simple, right? Because we already need R for the potential energy. So this whole thing, I'm going to write it again. The electron Hamiltonian, which was negative h bar squared over 2 times the mass of the electron times this x squared plus d squared dy squared. Remember, x, y, and z is now just the coordinates of the electron because we don't have to worry about the proton. And then we have this negative e squared over 4 pi epsilon naught r. This whole thing comes out to be, this part doesn't change, but instead of x, y, z, we have something in terms of r, theta, and phi, and this is what it looks like. 1 over r squared times ddr times r squared ddr, so let's use square brackets here, plus 1 over r squared sine theta dd theta times sine theta dd theta plus 1 over r squared sine squared theta times d squared d phi squared. So I know in Cartesian coordinates, this looks simple. The second derivative of x plus the second derivative of y plus the second derivative of z. But when we move to polar coordinates, it becomes so much more complex. But I promise you, it will make life easy. So that's this part here, and then we need the potential energy, which is just this 4 pi e naught r. For those of you wondering, this operator here in polar coordinates is exactly this stuff in square brackets that I wrote here, which I'm just going to write again. It's also in your textbook. But yeah, just so that you have it, that's what it looks like. There we go. So that's what that operator is in 3D polar coordinates. And now if you look at this, there's r, there's theta, there's phi. So when we solve for the wave function, it should be in terms of r, theta, and phi, or r, phi, and theta. Just 3 different coordinates, not x, y, and z now, r, theta, and phi. Remember, this is going to be the wave function for the electron, but it's the only part that we care about because we're going to say that the nucleus is fixed, doesn't really move. So hopefully, I'm not going too fast. If I am, please let me know and I can slow down. But I think at this point, we've done this a few times already with different examples. The hydrogen atom is just another example. So, but yeah, let me know if you want me to slow down.
I have a question.
Go ahead.
So the last part of the Naglo squared, why are we taking 1 over r squared sine theta and then multiplying it by the second derivative of phi?
Here?
Yeah.
Sorry, I hear feedback. That's just what this comes out to be. D x squared, d squared dx squared, d squared dy squared, d squared dz squared in spherical polar coordinates.
Okay.
I think we went over what x, y, and z are in spherical polar coordinates when we did the 3-dimensional rigid rotor. This is just what it comes out to be. In a 3D rigid rotor, a particle and a sphere, it looked a little bit simpler than this because r was fixed before, if you remember that. But this is not the case for the hydrogen atom because we don't know what the radius of the electron is. So the radius could be anywhere from 0 to infinity. So actually, let's look at that. Let's look at that here. So r is the radius, right? But we don't know where the electron is. So I mean, this is the electron right there, right? We don't know where the electron is. So r could go anywhere from 0, which means it's right on top of the nucleus, all the way out to infinity. We're not going to make any assumptions about how far away it is, right? We know phi goes between 0 and 2 pi. That doesn't change from what we learned earlier. And theta goes between 0 and pi from what we learned earlier. Those are going to be the limits for when we need to integrate this stuff later on. And so these different terms that appear in terms of r that we didn't see before necessarily is just because r is not fixed. R can vary now.
Okay.
Sounds good?
Yep.
Cool. So this is our wave function. And this is what we need to try to solve. So the hydrogen wave function. Doesn't have 2 eyes. So that's our wave function that we need to solve for. From here on out, I'm just going to drop the EL in the bottom there. When we write the wave function, right, we know it's going to be the wave function for the electron, not the wave function for the whole atom, the proton and the electron together, just the electron. So we said the wave function should should depend on the r and phi and theta, like that. But earlier when we solved similar problems, 3-dimensional particle in a box, rigid rotor, all of these things, we said that more than one coordinate is even too complex for us to handle, right? And we separated out. Remember when we had for 3D particle in a box, we had wave function for x, y, z, but we said let's call it one function of x multiplied by another function in y times another function in z, kind of like that. And we did the same thing for even like 3D rigid rotor. We're going to do the same thing here again. Instead of one big function of 3 different variables, we're going to multiply 3 smaller functions of just 1 variable each. So for r, we're just going to call the function capital R, right? For the phi, it's going to be capital phi, like that, and then capital theta. So instead of one function, we're going to assume that we're going to have 3 different functions, each of 1 variable, alone. And remember, this idea was called separation of variables. In case you're wondering, the reason why we can only solve the Schrodinger equation for hydrogen atoms and nothing else is because we can separate the variables like this and still solve it. Whereas once you have multiple electrons in there, we can't separate the variables as easily as this. And so, well, we can't solve them, at least not analytically. We can get approximate solutions for them. All right, so we have 3 parts. And what do you know it? The reason why we went through all of the different types of examples that we did before getting to the hydrogen atom is because we know what those three parts are, or at least most of those 3 parts. For example, the part that depend on phi, right? We looked at that before. It depends on a quantum number ml, and it looks like this, 1 over square root of 2 pi times e to the I ml phi. Should look familiar. The part that depends on theta, right, depends on 2 quantum numbers, L and ML, and they are the associated Legendre polynomials that I showed you earlier. So these 2 parts that depend on just theta and phi, we looked at exactly, they're identical to particle on a sphere. Because if you think about it, a particle on a sphere is just like an atom, a hydrogen atom, except the electron is fixed on a sphere, like the radius is fixed. The only difference is for a real hydrogen atom, the radius is not fixed, the radius is allowed to move about. So now all we need to figure out is, what is this radial function? But I'm getting ahead of myself. I said earlier too that when you add these 2 functions up together, so you have phi times ml, sorry, not times ml, phi with quantum number ml and theta with quantum numbers L and ML, that's the same as the spherical harmonics, right? If you combine them together, you get spherical harmonics. And just so that you remember, L can be 0, 1, 2, and so on, whereas ML goes is 0 plus or minus 1 all the way up to plus or minus L. And these limits are going to change a little bit once we talk about R. None of this has changed from what we learned before with particle on a sphere. All right, so what is R? And of course, all of these problems, mathematicians have solved for us. So I'm not gonna let's go over the math, let's figure out how we get them. Mathematicians have figured them out for us, and we found that R depends on 2 quantum numbers, N and L, right? And they're called the exponential associated Laguerre. I don't know how you say these names. I think it's French. Laguerre, Laguere polynomials. It actually took me a while to track down what these look like. As weird as this sounds, it took me a while to track them down because your textbook has a set, and then the other textbook that I'm also using to get your lecture note has a set of R functions, and they were different. And then I Googled online to figure out which one of the two is correct. And I get a third set of these Laguerre polynomials that were even different from the first two. So it took me a while to derive and track these down and make sure they're all correct. But these exponential associated Laguerre polynomials, they look kind of like this, right? They can be thought of as coming from a set of polynomials times an exponential function r over n times a, where a here for our example is going to be 4 pi epsilon naught h bar squared over the reduced mass, which for most cases is just going to be the mass of the electron, times e squared, which is the elementary charge. And this first, so this is the exponential part, and that's why it's called exponential associated. And this is the Laguerre polynomials that you might see in most textbooks. Laguerre polynomials. And when we do this, we realize that these quantum numbers n could go from 1, 2, 3 up to infinity. But when we use it, we need to limit L, right? It starts from 0, 1, 2, 3, and so on. But L gets limited. L gets limited up to n minus 1. Or you can think of it as L must be always equal, must always be less than n. So by
Sorry,
using,
what is E here for A, the charge or elemental charge? Okay.
yeah, this is elementary charge. And this here is the reduced mass. And just for completeness, remember ML could be 0 plus or minus 1 all the way up to plus or minus L. So this R I said is called the exponential associated Laguerre polynomials, and it's a mouthful, right? Like, I don't even know who this Laguerre guy is. It's too much. So I'm just gonna call this, going forward, I'm gonna call this the radial wave function. It's easier, radial wave function. So what does it look like? Let's look at it. So the radial wave function, because we already know what this and this, what they look like, what they are. We did it earlier. This is the first time we're encountering this radial part, radial wave function. So let's look at it. We said it'll depend on two numbers, right? There's n. It also depends on L. And so we want to see what n and L comes out to be. So this is R of n and L as a function of R, right? All right. So n starts at 1 and could go up to infinity, whereas L should start at 0. So for n equals 1 and L equals 0, what does the radial wave function look like? Well, it's 2 times z over a to 3 over 2 power times e to the minus z times r over a. Remember, a is, I did it up above here, it's 4 pi epsilon naught h bar squared over the reduced mass times e squared. Z is the number of protons. So I'm generalizing this Z for number of protons. Why? Because even though we did it for hydrogen atom, where we have 1 proton and 1 electron, Actually, we could use this, we could generalize this to any system with one electron. So any system with one electron. For example, hydrogen atom has one electron, but a helium with a +1 charge has one electron, where here Z would be equals to 2. Lithium 2 plus, right? Z would be 3. It's the number of protons. Hydrogen, helium, lithium, beryllium 3 plus, right? Z would be 4. Any system, any atom or ion rather, with just one electron, we can use this for. We just have to use the appropriate value for Z. A is this big complicated thing up here. And so this is the first radial wave function. All right. When n is equal to 2 and L is equal to 0, the radial wave function looks like 2 times Z over 2a to the 3 over 2 power times 1 minus ZR over 2a times e to the minus ZR over 2a. When n is 2 but L is 1, the radial wave function becomes 1 over the square root of 3 times Z over 2a times 3 over 2. Of course, in an exam, I'm going to give you all of this, right? But it's nice to have them down. And they might be slightly different than what you see in your textbook because, like I said, I had to track these down and figure out exactly which one should work with which one. And the ones that I'm giving you are already normalized. So like the wave function should be normalized and all that. Let's go up to 3. So n equals 3, L equals 0. The wave function becomes 2z over 3a to the 3 over 2 times some stuff, 1 minus 2zr over 3a plus 2 into zr squared over 27a squared e to the minus zr over 3a. We have n equals 3, L equals 1. The wave function becomes square root of 32 over 3 . So as I'm doing all of this and you're writing them down, you should in your head be thinking, oh, I should now be able to write any hydrogen wave function I want for at least the given any value of NL or ML that I've given you. So here we have n equals 3, L equals 2, and the wave function becomes, it gets more and more complicated the higher and higher you go, of course. ZR over A squared e to the minus ZR over 3a. I'm going to stop there. So we have n equals 1, 2, or 3, and and L equals all the possible combinations for those.
Is L here the same L as it is for what we did previously, like
Yes,
the spherical harmonics?
yes. So the L here has to coincide with that L. That's why I called it the same thing. And it should sync up with the ML values that you're given as well. All right, so you have all three parts. I'm going to leave a little bit of that there. You have all three parts. The wave function has three quantum numbers, M, L. No, let's start with the bigger one. N, L, and ML, which basically you can think of it as comprising of three parts: a radial part with N and L, a theta part with L and ML, and a phi part with just ML. And you now know what all those three parts are. So my question to you is, write the hydrogen-like wave function for an atom or ion with Z number, I'm just keeping a general, Z number of protons and with N equals, let's say 2, L equals 0, and ML equals 0. So let's see if we can put that together. Using the stuff that I gave you. The answer is also in your textbook, but I'll show you how to write this answer simply, and then how complicated your textbook makes it. Let me know when somebody thinks they have it written out. Once a few people lets me know they're done, I know I can like move on. No, we haven't written it yet.
I think I have the components. I just need to combine them.
And don't try too hard to combine them. I mean, you know, sometimes when we try to combine them, they end up looking more complicated. All right, let's work this. So we're looking for a wave function with quantum numbers 2, 0, 0, right? N is 2, L is 0, ML is 0. We know there should be, it should have 3 components, R with 2, 0, right? N and L. Theta with 2 numbers, 0 and 0. And the phi, well, the phi part doesn't really change. The phi is always 1 over square root of 2 pi times e to the I ml phi. But if ml is 0, this part goes away. So it's just 1 over square root of 2 pi, like that. So that's the phi part, right? If we look up on the stuff that I just wrote, R20, N is 2, L is 0. That's this guy right here. So to all of that. So I'm going to write that again. So that part becomes 2 times z over 2a to 3 over 2 times 1 minus zr over 2a e to the minus zr over 2a, right? That's the r part. Now for the theta part, right? The theta part, if we look back all the way back to when I gave you the associated Legendre polynomials, for 0, 0, that is just half times the square root of 2. I don't know if you recall that. And then we have this, the phi part, which is just 1 over square root of 2 pi, right? And I just want to simplify this a little bit. So the 2 here will cancel out with the 2 there. The square root 2 here cancel out with the square root of 2 inside there, right? So what we're left with is z over 2a, 3 over 2, right? That's from there. 1 minus z star over 2a. We have this 1 over square root of 2 pi. Sorry, 1 over square root of pi because the 2, I'll put this back here, 1 over square root of pi. And then we have this part here, e to the minus zr over 2a. And that's it. That is our wave function for those different quantum numbers. This does not match what you have in your textbook. Your textbook has this written a lot more complicatedly, but let's see if we can match it, because why not? Because you might be thinking, Professor Chulai is teaching you wrong things. It doesn't match what you have in the textbook. So what I'm going to do here is I'm going to multiply everything inside this little parentheses here by 2. And then I'm going to divide by 2 outside to make life to cancel out that 2. So we have a half times 1 over square root of pi. This part stays the same, z over 2a, 3 over 2. But then I multiply everything inside this parentheses by 2, right? So it becomes 2 minus zr over a, right? Because the 2 cancels out with that 2. So this is what I end up with. Okay, what else do I do? I'm going to take this cube here and put it inside of the parentheses. So 1 over square root of pi. This becomes z cubed, and this becomes 2 cubes. That's 2 times 2 times 2. That's 2 2s, 4 2s, 8a cubed. And this becomes just a half outside there. All right. What else would I do? I'm going to take this square root, because this is to the half power means square root. So I'm going to take the square root and put it inside there. So z cubed over 8 pi a cubed, all of this to the half, 2 minus zr over a. All right, what am I going to do next? I'm just going to do a, all right, I'm going to change the stuff in here to be, instead of 1 over 8, I'll make it 2 over 16. That's the same number, right? Where am I going with this? I just want to show you how your textbook came up with the numbers it has. E to minus zr over 2a. And then what this allows us to do is basically say, hey, the square root of 16 is 4. So I can take the square root of 16 as 4 and take it outside. So the half times 1 over 4 becomes 1 over 8, right? And then everything else in here becomes 2z cubed over pi a cubed to the half. And then this part stays the same, zr over a, and then e to the minus zr over 2a. And that's what your textbook has for that. But it's exactly identical to what we have up here. To me, it just looks a lot more complicated. But why I'm showing you this is I want you for practice, try putting together various wave functions for different numbers of n, l, and ml. Just play around with them. But the only way to check your answers is to compare it with your textbook, right? So you can like play around with it to see if you get the same answers as your textbook. Does this make sense? All right, so just play around with different values of n, l, and ml when you have time, just to see that whether you can match the values that are given in the textbook. Okay, so now we wrote the Hamiltonian. We figured out what the wave function is. There's only one part left to figure out from the Schrodinger equation. What is the energy? So let's look at the hydrogen like energy. Any questions about the wave function before I move on? No? All right. So it turns out, I'll write this stuff that I did above there again. The wave function has quantum numbers n, l, and ml, right? N, L, and ML. But it turns out the energy only depends on one of those numbers. The energy only depends on one quantum number, N. And again, we're not going to derive how we get the energy, but that energy is just negative z squared. Remember, z is the number of protons. E to the fourth, E is the elementary charge. Mu here is the reduced mass over 8 epsilon naught squared h squared n squared. That's the energy. Mu here, I'll put a little note that there's the reduced mass. Typically, you can just use the mass of the electron and that'll be all fine. So mu is the reduced mass, E is the elementary charge, right? I'm just going to write it again. Epsilon naught, we looked at this earlier in the semester. It is a permittivity of free space. It's 8.854 by 10 to the minus 12 coulomb squared over joules times meter. What else we have? We have H, which we all know is Planck's constant, right? To the minus 34 joules times seconds. And mu is a reduced mass. And to make this all work, SI units for that would be kilograms. So here is my question for you. What is the energy in joules for the lowest energy state wave function, or eigenstate as people call them, of the lowest energy eigenstate for a helium plus ion? So let's see if you can work that one out. Sorry, there we go. Um, since most times the reduced mass will be the mass of the electron, use the mass of the electron, and the mass of the electron is 9.109 by 10 to the minus 31 kilograms. There we go. If you have answers, you can type it in chat or shout it out or any of that stuff. Remember earlier, we stated by convention, because of how the potential energy is, negative energy means that everything's good and attractive, and positive energy means everything's repelling. So if you get a negative energy, that's exactly what you should get, right? If an electron had a positive energy, it means that it was being repelled by the atom. No answers yet? Okay. And I think that is correct. So how do we get that? For those of you still working. So we know that the energy is exactly that formula up there. Negative z squared e to the fourth. The reduced mass, we'll just use the mass of the electron. 8 epsilon naught squared, h bar squared, n squared, right? Couple of clues. Here, we're looking for the lowest energy eigenstate. So the lowest energy would be n equals 1. That's the lowest energy. And we're looking for a helium plus ion. So number of protons, z is equal to 2. Right? So at this point, all we got to do is plug those things in. We get negative, z is 2, so 2 squared times e is 1.602 by 10 to the minus 19 coulomb squared. Nope, sorry, fourth power, right? Mass of electron, 9.109 by 10 to the minus 31 kilograms. On the bottom, we have 8. Epsilon naught is 8.854 by 10 to the minus 12 coulomb squared over joules times meters, but that's squared. H is 6.646 by 10 to the minus 31 joules times seconds, and that's squared. And n equals 1, so we have 1 squared. Now, just to show you the unit stuff, I'm going to take all the units. So c to the fourth power, that's c to the fourth power. Kilogram, that's kilogram. C squared to the squared, that's c to the fourth power, over joules squared times meters squared, right? And then here we have joules times second squared, so that's joules squared times second squared, like that. And then the C4 will cancel out with the C4, joule squared with joule squared. And then we have kilogram meter squared, right, per second squared, that's all joules. Kilogram meter squared per second squared, that's all joules. So our answer will come out to be in joules. You plug that all in your calculator. If you get a divide by zero error, did anybody get a divide by zero error? Yeah, because these numbers are so tiny that when you start to square them, you get really, really small exponents, and your calculator doesn't know we're working with atoms where things could be really, really small. So it's like, that all comes out to be practically zero. So you need to, well, the way I do it is you look at all of the sort of the first parts before the 10 to the minus whatever, multiply and divide those first, and then deal with the exponents. And that's one way to get around the divide by zero error. But all of this for me comes out to be negative 8.716 by 10 to the minus 18 joules. And we're looking at E1, right? Because n equals 1. And there it is. Any questions on that so far? So you can plug in any values of n, and you can pick any number of ion where you only have one electron and try to figure out their energies. But in general, we are interested in energy differences, right? Because remember, all of this ties back into spectroscopy, where spectroscopy, we're dealing with photons emitted or absorbed, right? So we need to look at energy changes. And so the energy change would come from the energy of some final level, let's call it NF for final, minus the energy from some initial level, right? So if you write this all out, for the final level, the energy would be z squared e to the fourth, the reduced mass, times 8 epsilon naught squared, h squared, and f squared. And from the initial level, it's the same thing, right? Except it's from the initial level squared. So if we sort of put all of the stuff together, it comes out to be, and here we have 1 over the final level squared minus 1 over the initial level squared. Earlier in the semester, maybe within the first week of the semester, we looked at the Rydberg equation. And we said the Rydberg equation, right, assumed that electrons were fixed at some radius and they were rotating, and the energy change comes from the Rydberg constant for hydrogen. And it looks pretty much identical, right? Except for hydrogen, Z should be 1, because this is what hydrogen means. Z should be 1, and mu should be the mass of the electron, like that. And so if we calculate the Rydberg constant using that, we get that the Rydberg constant is e to the fourth times the mass of the electron divided by 8 epsilon naught squared h bar squared. So we've come full circle. In the beginning of the semester, we looked at how spectrum for hydrogen could not be explained by classical physics. And Rydberg came along and he was like, or Bohr actually came along with the Bohr model, right? And say, let's just assume that the electrons are fixed in certain orbits. We gave them some values for n, and then they calculated the energy differences from that, and it matched perfectly. Except there was no explanation for why electrons were fixed in orbit or any of that. We've come full circle where we're now describing electrons as waves, not as balls of charge fixed in an orbit. We made no assumption about the orbit. We said r could vary from 0 to infinity. Didn't matter, right? But when we solve for the energy, we get the exact same energy equation out. So Rydberg and Bohr stumbled on that energy equation by accident, but it's the exact same energy equation we got from quantum mechanics without making any assumptions at all, except for the assumptions of quantum mechanics. So we've come full circle. We're starting to explore spectroscopy now using quantum mechanics. And I will stop there. Then when we come back, we'll use this equation to calculate energy differences and wavelengths and stuff from hydrogen atoms and other types of atoms when we come back. Any questions on what we've talked about so far? Nope. All right. So we'll see you on Thursday. I'll have your exam to return, and your bonus question stuff will be entirely optional. All right. Enjoy the rest of your day, and I'll see you later.